excited to talk to you today, tell you a little bit about some of the research that we're doing here at UC Santa Barbara, primarily with the Institute for Energy Efficiency and the Computer Science Department. I'm a professor in computer science. As we heard from Mark and Brent, there was a lot of talk of IoT, and I really wanted to kind of push on that end of it. So I'm going to talk today about the Internet of Things, where we're embedding tiny little sensors and computers in ordinary objects in our lives. Everything from this platform to this carpet to this building to these windows to your clothes. All eventually will probably have little sensors and little computers. And it's not just that these IoT devices are collecting information. They're making all kinds of different measurements, producing vast amounts of data, of information. But they're also then working together, interacting and communicating with each other, the different devices in our environment, to solve problems. And in order to do that, they use the data that they're collecting, and then they're performing analysis and processing that data to make these decisions automatically without humans in the loop. So the vision that you hear about the smart cities and the smart agriculture and the smart transportation and the smart farms and the smart dogs and the smart cats and everything from self-driving cars and artificial intelligence, it's all really about collecting vast amounts of information and processing it in ways that we can solve problems without humans in the loop. So if you think about IoT, there's a couple things you need. You need to have devices that are really tiny and that can sense and be energy efficient and that can be embedded in our environment, in our physical infrastructure. And we have that. We have researchers working on that. We have companies making great inroads in that. You then need to have software systems that collect and aggregate and fuse the data that's being collected to make decisions, so machine learning and data analytics. And also, fortunately, we have that. And that comes from the last decade of cloud computing and data analytics that have been driven by electronic commerce and entertainment. In the large-scale internet computing space, it's really been about large internet providers giving us services that we use online or via our cell phones and apps to give us instant access to information, to give us recommendations about who to meet and what to buy. These companies have given these online services to us for free. At the same time, they're collecting all of this information about us as individuals. The data they're collecting is both personal and private and professional. Everything about our lives is being collected, and these companies use this data in order to refine our experience, make our lives better, but also to help encourage us to buy more effectively and more efficiently. What's interesting about cloud and data analytics for the IoT space is that these companies have matured this technology because they have been driven by business incentives to the point where we can use it for other things. So on the cloud end, these companies are using vast amounts of information and putting it into very large-scale servers. We know how to manage warehouse-sized computers. We know how to run them. We know how to use them and share them with virtualization, as Mark was just talking about. We also then know how to do the analytics, the machine learning, the artificial intelligence that you hear about. That's all just complex but well understood math and statistics that have really been pushed to the forefront of technology and then written as code so that the computers can do all of this for us. And another thing that's really interesting about what's happened recently is for these companies to be effective, or the reason why they're so effective is that the analytics that's being done now with the scale and size of the amounts of data have given us the ability not just to predict and generate inferences about groups of people or trends in society, but about you as individuals. They're able to tell you when you want to buy something, what you will buy, and what you will pay for it. And that's extremely powerful. And that's exactly what we need when we move to a society an era where we want our infrastructure, our railroads, our cars, our farms, our houses, our buildings to become smart themselves. We really need the ability to process this mass amounts of data and answer questions in an autonomous way. And not just answer questions, but to actuate and control and automate the systems and the physical spaces that we live in. So we have cloud and data. We have data analytics, we have cloud, we have machine learning. We have the ability to embed tiny little devices and sensors into our physical infrastructure. But IoT's been talked about for decades, and it really hasn't come to the fore. It's been slow. It hasn't, we have the very beginning of some of this, but it's not widespread, and it's not ubiquitous, and it's not even that effective in many ways. And so our group asks why. What's going on and what needs to change from a research perspective so that we can make advances such as the ones that we envision will change our lives and our societies. And because Brent spoke ahead of me and I'm friends with Brent, he stole all of my good slides. So I had to quickly rework. But it's the same points that both Brent and Mark hinted at. And the idea is that the cloud and the internet were not designed for IoT. The cloud and the internet were designed for people, for humans. It's our entertainment. It's our content delivery. It's our e-commerce that the cloud and the internet have been tailored and specialized for. So what do? We have, Brent said about 1 billion cell phones, but there's about 7 billion people on the planet. Studies show about half have internet connectivity. So 3.5 billion people at any one time using the internet. And what are we doing? We're downloading content. Sure, these big companies are collecting information about us as we download content, but the primary use of the networking infrastructure is from the cloud to the individual, to the edge, where the people live. Okay, and 3.5 billion sounds like a lot, but as everyone was telling you, that's nothing compared to where we're going with all of the devices, all of the objects in our lives that are soon to be connected. And these devices are not downloading content. They're not watching movies or videos or TV shows. They are producing data and we're shoving it back up the network. And that is just broken. We cannot use the infrastructure we have designed for the opposite use to serve a purpose like this. So this is one of the impediments that we're going to need to overcome. It's right dominated. The way you overcome it is with edge systems. You create computer systems made out of anything. Intel NUCs, you can have a dozen of these little boxes, don't cost very much. Produce a small distributed system. You can make that look exactly like Amazon's cloud today, or Google's cloud. And you can run that at the edge, and instead of moving all that data from these devices to the cloud, you move it, you put the edge systems out in the wild, out at the edge, and you only move the data as far as they are. And then, but what's interesting here is the edge systems have been around forever. Content delivery networks you've heard of, I'm sure, CDNs. This is not content caching. This is going to be data caching, and it's also going to be analytics that we have to perform. What do we want to do with this? We want to answer questions. We want to drive actuation and control. In order to do that, we have to do really intelligent things out at the edge, and that's actually hard. It's not caching. It's actually computation. It's analytics. But we do know how to do this. What we're really doing is instead of moving all that data to the cloud, we're moving code, which is tiny, from the cloud to the edge. And that code then is the intelligence that's going to drive the analytics and the actuation and control that's going to be data-driven out at the edge. So we know how to do this. You download apps on your phone a lot, and it's the same model. You produce software, we download it to the edge systems, and then they can run it. This would just be looking more like analytics code or machine learning code that would be downloading. The other thing to notice on these edge systems is that they're resource constrained compared to clouds. So they're like small baby versions of clouds. In fact, you can have a bunch of these Intel NUCs as your edge systems, or even a rack of servers, as Brent was pointing out. But you can also have these little guys. This is a Linux system, Raspberry Pi Zero. put a bunch of these in. It can still do amazing analytics, statistics, data aggregation, fusion on a tiny little device that's really energy efficient. Okay, so what's going to happen is you're going to have edge systems, and maybe it's not just the edge and just the cloud. You're going to have something that is going to be tiered, because you want to think about IoT as you solve the problem and you move the data only as far as it takes to solve the problem. So if you have this room and we want to adjust the light, or you want to adjust the sound down because I'm very loud, the building can notice that, and it doesn't need to, the data doesn't need to leave this room. The actuation and control can happen automatically in this room. But say you want to maybe look across Santa Barbara County and decide how we're going to manage water resources over the next year to conserve water. Well, you're going to need information at the county level. So maybe you need a regional system that's able to aggregate and fuse data across an area. And then, of course, if you're doing something globally, the public clouds are ideal for this. And so you only want to move data as far as it's going to take to answer or solve the problem or actuate the system that you want. Okay, so if that's our model, that's the future. How are we going to write code for that? How are we going to write these analytics programs? How are we going to develop that software? It's already super hard to write code for the cloud. And the cloud is one big warehouse-sized computer. And it's not just one cloud. Amazon's cloud is very different from Microsoft's cloud, is very different from Google's cloud on purpose. They don't want you to move from cloud to cloud. It is in their incentive that you stay, that you have some gravity pulling you towards their cloud. Okay, so there's diversity in the clouds. There's diversity in these edge systems and these regional systems. The capabilities are different necessarily. If I'm running on this, that's very different than if I'm running on this. We don't want you to have to become a computer scientist in order to program this. But that is why I believe this has been so slow. No one can program this. It's even the super experts are unable to. So we're going to need to make advances in science, in computer science, to make this simpler because of the heterogeneity. Because of the capabilities are different, the energy use is different, the footprint is different, the size is different, the hardware is different. How often they need to be up and down is different. Not to mention, how are you going to deploy your software? Even if I taught you how to write a piece of code for this, how you get it to that device is highly varied and extremely hard, and really hard to do automatically today. And this is why I think the innovation in IoT and the promise of IoT just hasn't gotten close. So, and I want to go one step further. Not only do we, the computer science experts, need to be able to program this, but I'd argue that novices need to program this. Scientists who aren't computer scientists need to program this. You all, everyone in this room, should be able to ask a question about a piece of data that's being collected about an environment that you're interested in and get an answer. But if you're unable to do that, then it's going to be extremely this is going to be much, much less useful. It's going to take a long time for innovation to happen. So not only do we need to be able to program a system like this, we need to be able to program it in a way that a lot of people who aren't computer scientists can program the system. We have some hope because the applications we care about in this setting are really analytics applications. They're statistics, they're machine learning, there are some neural networks, and so you could see that as semi-focused. It's not general purpose, and it's not total special purpose, but if we can focus on a set of application or an application domain such as this, we may have a chance. And so that's kind of the perspective that we take. We design systems that make it portable to execute code that you write once, and it runs across any of these systems. Everything from a tiny microcontroller all the way up to a cloud, super cloud. They're energy efficient. If they're resource constrained, some of these devices won't even be plugged in. They'll have a solar panel or be attached to some other form of energy, like a battery. And we have to be able to use them appropriately. We have to be able to automate deployment at scale, 75 billion devices. That's just completely overwhelming when you go to think about how you're going to write an application that's going to use these devices. And we have to make it so that you can ask questions with the next generation of machine learning and analytics techniques that are coming on board. So how do we do that? Well, our background is in cloud computing, as I hinted at. So we're going to take a page out of the playbook of cloud again. And what cloud does when they have infrastructure, hardware and software, that lots of people use, and they want to get more people to use it, what they do is they provide an abstraction layer that they call as a service. What's really happening behind the scenes is that there is a management layer, a software layer that's managing a lot of the complexities and the heterogeneity and ugliness that happens behind the scenes that we all need to use, but we all don't want to know about. So infrastructure as a service, for example, allows a cloud company just to hand you a server. Log in, do whatever you want with it. You don't care where it's running. You don't care, where it lives. You just know that you want a server and you want to set it up, and you can do anything you want with it. Clouds take this a step further. They say platform as a service. If you and I have 100 servers, and we're going to do some analytics. We're going to install Spark. We're going to install HDFS, a distributed file system. We're going to install all those runtime systems, R and MATLAB and Python, and databases, because we got to store some state. But think about all that. It would take us weeks to get a distributed system all working together, efficiently operating. And we're doing the same thing. You have to set all that up. I have to set all that up. We all are miserable setting that up. And so what the cloud says is, no. Put that in the platform. Let the system automation do that for you, and then you focus on the innovation. You focus on just the piece that is novel and new and different and your idea. Everything else we know how to do. Don't waste time. Let the platform do it for you. So this is the model we take. We are designing a platform called Spot, Software Platform of Things. And what it's doing is to create this abstraction layer that hides all of the gory detail behind the scenes of all these disparate, heterogeneous systems. The Spot platform is unique in that we have to make it super easy for experts and non-experts. So what we're going to do is something that Mark hinted at, is we're going to use functions. Instead of you writing a big old application, you're just going to write a function. You're going to write a function. It's going to execute on the platform. And wherever the platform executes, your code executes. So you write it once in a high-level language, any language you like, and we can make it work across these systems. And the platform takes control or handles for you all of the hard, gory stuff of where you place things, how you move things, where's your data. You don't need to know any of that. You need to think about innovation. The functions are triggered by events. So when you write a function, you think, okay, I want to run some code when my data is ready. So you say, this is what it means when my data is ready. And when that occurs, the system, the platform, invokes your function. And this is really nice because everybody can understand event-driven systems and responding to events. And you just focus on one job. What do you do when that event fires? Right? So we're trying to simplify, and so another thing that you need if you do this is state. So if you have a function and you're operating on some data, if the function goes away, your data goes away. And so there's going to be, and you could put it in the database, but do we really want to install a database and manage a database? One idea is, that's fine, but you have to learn SQL and all the overhead of databases. Or how about you just have a variable, an object. It's in your code already. What if we can give you an object that would then be persisted automatically when the function left, when the function went away? Now you have some variables that you don't need persistence. Those are just normal variables. And then you have these special variables, we call them WOFs, wide area objects of functions. And WOFs are these way of having a data structure in your program that automatically persists. And what's nice about it is you can make copies of it. So you have durability across the system automatically by the platform. And then lastly, we need to make it look cloud-like. When you go to the cloud, nobody writes code anymore. I teach undergraduates all the time. They show me what code they write. It's a couple of lines, and they're all accessing services somewhere else, services in the cloud through APIs, application interfaces, and application programming interfaces. And so what you do is for your functionality, you want to do some analytics, you get your data from somewhere, do an API. You use your data, you process your data, you get it all ready, you package it up, you hand it to a service. Let's say an image processing service in Amazon. Amazon comes back with a classification of what your image is, right? There's like 4 lines of code for that. Get my data, prepare it, send it to Amazon, get my answer. The way code is written today is through APIs to services. And so it's really key that we're going to be able to, across this distributed system, run the analytics platforms that you need, the libraries that you need, the systems that you need. So we study how do we make that happen, and how do we make that happen effectively and efficiently, and all behind the scenes. Sticking on that idea of services, we turn devices into services. So instead of having 75 billion devices out there where you have to name each one and know where each one is and specify which one you want and what it does, no, you say something like, hey, I need some temperature readings from this building, from this room. If you can specify that, why don't we just make the devices, one or more, that give you that information a service? We know how to program against APIs. We know how to ask Amazon for an analytics package for image processing. How about we implement APIs that allow us to have devices that we just say, give me some data, and you get it. And so we have this system where we kind of flip the world, if you're from a computer science perspective, that where devices are no longer clients, but they're actually servers. They provide services. And then we have these edge systems, here they're called edgistries, that sit in the middle of the devices, sit in front. And this allows us to do very clever things with security and privacy and efficiency and placement. And when devices go bad, you could swap them out. It gives us a shim layer that allows us to have some flexibility and scale when things get big. The other thing is, these edgistries and these devices as services, they all work with Spot. So you want to write a function, you specify your APIs in your function, you ask for the data appears. When the data appears, you get triggered. Your function calls another API for analytics, you get your answer. You can build pipelines, you can build the same analytics that we do in the cloud now. You can just do it easily at the edge. That's our vision, that's what we're working on. So we prototype this. And there's some cloud companies, Amazon and Microsoft, who are working on something similar, but for Amazon and Microsoft. Our stuff, notice, will work in Microsoft, in Amazon, in Google, anybody else who comes along, and work across clouds. So, but it also works all the way to the edge on these little tiny microcontrollers all the way up to the cloud. And so we measured how fast we can do this. We want multiple replicas of your state. So these objects that you care about, that you want replicated and you want to stick around. So we're going to have a number of replications of that data. Amazon and Microsoft automatically give you 3 copies of all your data. And then we just do a very simple test to kind of move data through the system. And it takes about 500 milliseconds to do it with Spot. Same exact setup. Can't do exactly the same as in Amazon and in Microsoft as what Spot can do. But on the order, it's much, much slower. So this is much faster. And fast means low energy consumption in our space. The other thing is, in addition to energy consumption, this model of devices as services gives us this ability to do security and authentication in a new way. And we can do it because of this model with 3 to 4 orders of magnitude less energy use than all the traditional models that exist today. So this is a real disruptor, a real change in view, and hopefully something that we can help spur innovation to start to take advantage of the tremendous potential that IoT and cyber-physical systems offer. It needs to be at the edge, and we need to have intelligence at the edge, not just sensing and caching. We have to have intelligence. We have to have analytics. All the analytics that you've ever want to do has to be able to happen at the edge. We need to have energy efficiency. We need to think of that as first class. We need to have low latency. If you want to actuate something at the edge, it has to happen fast when you want to actuate it. If you want the self-driving car to turn left, you can't wait till next Tuesday to get the answer. And our work is just starting to show that it's possible to do something along along these lines, and to actually produce a programming model that not only computer scientists can write code with, but all of you can. And with that, I don't do any of this alone. I have an amazing team, an amazing group, and amazing students. I'm super, super lucky and fortunate to be at an amazing place like UCSB. And I couldn't do that without any of my supporters as well. So thank you to all of you for listening, and I'll take any questions that you have.